Okay, so we're going to look at measures of variability. And so the first question is, why do we care? Why does it matter to us how much variableness, or how much does the data change? How much does it vary in various situations? And so I kind of want to point out a sort of a thought scenario, and then we'll actually go into numerical calculation. But imagine there's two lines in a grocery store, and one line, you know for a fact, is going to be waiting anywhere from 6 to 7 minutes. And the line next to you, as you're standing there for your 6 to 7 minutes, you see someone that gets helped within 2 minutes, someone has to wait another 8 minutes, someone gets a minute. Which line do you want to stand in? And it's sort of human nature to recognize that the more consistent line we're in, the more fair it seems. And the line where you get 2 minutes and 8 minutes and 1 minute and 10 minutes, there seems to be something unusual going on there. So why does variability matter? Well, it matters to us as far as how much does data change, and if it does change by a little or a lot. So let's actually take a look at how we measure variability, or at least a couple of measures. And to start off with, we're going to go back to our old friend, the mean, and we're going to calculate the mean of these data values. So if you recall from the last section, to calculate the mean, we're going to add them up and divide by the total. And I'm going to go ahead and pull Excel out because I think that's going to be a nice, easy tool for us to use. So let me do that. Okay, so the first thing I want to do, and again, if you don't have Excel handy, that's okay. You can just go to a calculator and you can type in all these numbers. But the first thing I want to do is I just want to input all of these values in so I can start manipulating them. And we're going to fill that table out. So that table is actually going to be nice to have in Excel so we can actually see all of these different, all the different things that are going to happen here. So 31 and 29. Okay, so from here, I want to total this column. So if you remember, the total is, I'm sorry, we want the average of this. So in Excel, we're going to use average, and then I'm just going to highlight all those numbers and hit enter, and I get an average value of 28. Okay, so the next part of our chart we're going to fill in is we're going to take each of these numbers, the 24, the 34, the 26, and I want to figure out how far are they from the average value. So I'm going to go 24 equals 24 minus 28 and get a number equals 34 minus 28. So I'm just going to come in here and literally just subtract each of these numbers from the mean and just sort of keep track of how far off of the mean are they. Because remember, we're trying to come up with a measure of variability. How much does each individual observation differ from the expected observation of 28? So I'm just going to fill this chart in. Oops. Now, interestingly, when we get done, yes, I just realized that 28 minus 28 is 0. Yes, I understand that. I'm just trying to be consistent. 21 minus 28, 35 minus 28, and 29 minus 28. Okay. Now, I want to sum this. So I'm going to add up all these numbers, and I just want to show you a slight problem that happens when I add all these numbers up. I get 0. So here's sort of the concern that we have. I would like to have a measure of how far off is a sort of a typical data point from the mean, but the problem is if I use that each number minus the mean, which tells me how far off it is, if I add that up and divide, which is what we're doing next, is we would divide that by the total number, I don't really get a number. And there's a good reason for that. So let's take this 24 for example. The way we calculate the mean by adding them up and divide by the total, that means 24 being 4 below, there's got to be another number that sort of would represent 4 above. Now, there might not be a balancing point. There might not be a 32, but that 37, that's 9 above, it can absorb the 24, it can absorb the 26. And so if we start partnering these numbers up, we can kind of see that there's just as much below the mean as there is above the mean. Okay. So what we do instead is we square these numbers. So this -4, 6, -2, 2, we're going to square those numbers. So we can do that one quickly in our head. -4 squared is 16. This is 36. -2 squared is 4. Remember, a negative times a negative is a positive. 2 squared is 4. 9 squared is 81. 12 squared is 144. Obviously 0 squared is 0. -7 squared is 49. As long as 7 squared is also 49, and then 1. And I want to add this up. Okay, so I get this number 375, which is the squared of the deviations. And then I want to be able to have an average for that. So I'm going to take this 375 and I'm going to divide it by, now it's going to sound a little strange to do it this way, but I'm going to divide it by 1 less than the total number of observations, so the total number of numbers. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. I'm going to divide it by 1 less than that, which is 9. And that'll give me 41.67. And then I want to go ahead and take the square root of this. So for Excel, there's a SQRT. You might just go to your calculator and do that. And I get a square root of 6.45. Okay, so we're going to talk about both these numbers here, but that should fill the chart in for us. Okay, so let me put some actual symbols on these formulas that we just did by hand. Before we took the square root, that's actually referred to as the variance of the data, kind of like the mean, and the median, the mode. This is just the variance, just another word that describes the relationships with the numbers. When we take the square root of that we get the standard deviation. Now, the standard deviation is what we typically consider to be the amount of variation from the mean. How far off is a typical data value from the average, from the mean itself, would be that standard deviation part. All right, let's go to define a few more new words. Range. The range of the data is when we subtract the highest value, the largest value, minus the lowest. High minus low gives us the range of a set of numbers. Okay. Then we have something called the lower quartile, or Q1. This is the 25th percentile in a group of data. The middle quartile, or Q2, is the 50th percentile Now this one we actually have another name for. This is called the median. The upper quartile, or Q3, is the 75th percentile. Five-number summary. Okay. So whenever we're asked to find a five-number summary, obviously there are five numbers we're going to point out. We want the low, then we want Q1, then we want Q2, Q3, and the high. And those five things constitute what the five-number summary. Graphically, we can illustrate the five-number summary using something called a box plot. We might have associated this as a box and whisker plot in grade school, but a box plot uses each of those numbers in the five-number summary to illustrate a certain feature of the box plot. So for example, we have a line on the low part, then Q1, Q3, Q2, and Q3 all form the box. So this would be the low, that would be Q1, that would be Q2, and that would be Q3. And then the high, we label the top piece on. So when we're constructing a box plot, we find the five-number summary, and then we draw a picture based around the numbers that show up for each of the summaries.